Okay, welcome to lesson 7.6, solving quadratic trigonometric equations. So again, I'm going to reference in this lesson how we solved quadratic polynomial equations. So this was like grade 10 math. What we did was we moved all of the terms to one side of the equation. So we set one side of the equation equal to 0, and then we factored. And then we set each one of those factors equal to 0 and solved. We're going to use that same strategy to solve a quadratic trig equation. So I'm going to go through a couple of different strategies to look for throughout these questions. In strategy 1, I'm going to look at common factoring. So in my first example, I've got tan x times cos squared x is equal to tan x. Remember that the first step is going to be to move all of the terms to one side of the equation. So I know I need to do this. I see a squared here on the cos. So I'm going to move everything over to one side. So I had positive tan x on the right, so I subtracted it over to the other side. Now that I've got this expression here, what I'm going to do is common factor this expression. I've got a tan x times something here, and then I'm subtracting a tan x times 1. So I'm going to take the tan x out, and then I'll just divide out and see what's left over. So when I take the first term and I divide it by tan x, I'm left with cos squared. And then when I take the second term, it's negative tan x. When I divide that by tan x, I'm left with negative 1. And now I've got a factored expression. So when I looked at this question, one of the things from the beginning that made me kind of uncomfortable was the mixture of ratios. I had a cos ratio and I had a tan ratio. So we don't love that. But when I did the common factoring, it kind of automatically separated the two ratios for me. We're going to look at some other strategies and other questions to help when there's a mixture of different ratios. But it's something to look out for. So now that I have it factored, the third step up top is to set each factor equal to 0 and solve. So I'm going to take the first factor, tan x. So either it equals 0 or the second thing that I'm multiplying by has to equal 0. I'm going to leave lots of space here. Okay, so first we're going to take a look at, well, what happens, like when is tan x equal to 0? So to come up with this, I can either think about what the graph of tan x looks like, or I can be thinking about rotational trig, in which case tan of x is the wide value of the point divided by the x value of the point. So I need that to equal 0. That means that the y value needs to be 0. Or the other way to think about this is tan x is the opposite over the adjacent. So thinking about drawing the triangle, you need the opposite side to be 0. So that means that the height of the triangle is 0. And so I have this, or over here on the opposite side, I have this. So there's two possible answers here for me. Sorry, actually 3, because I'm including the starting point of 0, but I'm also including the ending point of 2 pi. Those square brackets tell me to include them. So that tells me that x is either 0 or pi, or circling right back around, it could also be 2 pi. So that's the first side. For the second factor, setting it equal to 0, now there's a couple of ways you can solve this. You can, because there's only one term with x, you can actually isolate. So using our linear strategy from the last lesson, I can move the 1 over to the other side, and then I can take the square root of both sides. When you do that, you have to remember to take the positive and the negative square root. So that method will work. I'm going to use the same method that we have up here. It says that if you have a squaring, if you have a quadratic, you want to move all terms to one side, set it equal to 0. We already have that. And then you want to factor it. So what I see here is cos squared minus 1. This kind of reminds me of, like, what if I had y squared minus 1? Well, that's a difference of squares. And so that would be y minus 1 and y plus 1, right? Taking the square root of y squared at the front and the square root of 1 at the end, and then just switching or doing different signs for difference of squares. So I would factor this then as cos x, because I'm taking the square root of cos squared, and then it's going to be minus 1 in the one bracket and plus 1 in the other bracket. It's going to give me the same answer as the other strategy that I talked about. And then from here, I'm going to set each factor equal to 0. That's, again, my third step up here. So I either get that cos x is equal to 1, because that's the value that would make this first bracket 0, or cos x is equal to negative 1, because that's the value here for cos x that would make that bracket equal to 0. So I've got my two possible values for cos x, and so now I'm going to try and figure out, well, when is cos x equal to 1 or negative 1? So again, you can use rotational trig to help you with that, or you could be thinking about the graph of cos x. So the graph of cos x starts at a maximum and ends at 2 pi at another maximum. So I'm looking for, where does this graph have a height of 1 or negative 1? And so there are three possible answers. And I can see that they're at 0, at pi, and at 2 pi. And so I'll just state that over here. X then, for positive 1, x can be 0 or 2 pi. And for negative 1, x can be pi. Now I'm going to summarize what I found here, and I'm going to use a solution set. So I'm using set notation in my answer. Therefore, what I've figured out is that x belongs to the set, and there's actually only three possible answers: 0, pi, and 2 pi. These were all repeated on both sides, so I don't need to list them twice when they're repeated. All right, strategy 2, trinomial factoring. So I'm going to solve this guy here. It's a trinomial. I've got one term, 3 sine squared theta, the second term minus sine theta, and then the third term minus 2. So right away when I see the quadratic, I want to make sure it's set equal to 0, and it is. And now I'm going to try to factor. Now, I wouldn't always do this, but for this first question, because this is kind of uncomfortable for us, there's a lot of stuff going on. One of the ways you can simplify this, if you're struggling with trinomial factoring with some trig thrown in, is you can just replace the sine theta with a simpler variable. Now, when you do this, don't forget at the end of the question, you're not solving for y, you're solving for theta. So you have to come back and do that. So I'm going to let let y equal sine theta, and then my equation simplifies. So now instead of sine squared of theta, I have y squared. And then instead of subtracting sine theta, I have subtracting y, and then of course subtracting 2 equals 0. And now this becomes a little bit more familiar for me to factor. Now to factor this, I'm looking for what multiplies to the first number 3 times the last number negative 2. That's negative 6. And I want to add to the middle number negative 1. So my two numbers that I'm going to use here are negative 3 and 2. This is a decomposition question because there's a coefficient in front of the squared term. So that tells me that I'm going to decompose or split the middle term into two terms. And so I get 3y squared minus 3y plus 2y. And again, you could have those in the opposite order and you're going to get the same answer as me at the end of the day. And now that I've got four terms, we're going to group, and we're going to look for some common factors. So in the first group, 3y is the common factor, and then I'm left with y minus 1 when I divide out the 3y from both of those terms. And then for the second group, 2 is the common factor, and again I'm left with y minus 1 when I divide that out. You should have matching brackets, otherwise you made a mistake maybe when you selected these two numbers off to the side. Now that I've got that common bracket, I can factor it out, and then I'm left with 3y plus 2 when I divide out the y minus 1 from each of those terms. Okay, so now that I've got these two different brackets equal to 0 or two factors equal to 0, I can say that either the first bracket has to equal 0 or the second bracket has to equal 0. And then I'm going to solve these. Now that I've just got linear, I'm just isolating the variable. So either y equals 1 or y equals negative 2/3. All right, so now I've solved for y, but I need to remember that the question actually asked me to solve for sine of theta. And y is equal to, the question asked me to solve for theta, but y is equal to sine of theta. So sine of theta is equal to 1. So I'm coming back to the real question now. Now when sine of theta equals like 0, 1, or negative 1, I'm thinking about key points on the curve. So I think about a sketch of the curve. For sine theta, there's my curve. And I'm asking, well, when does this curve have a height of 1? And there it is at pi by 2. And so I'll say that my first angle, theta 1, is equal to pi by 2. And then I'm going to come over here, and same thing, instead of y, I know that y is the same as sine theta. And I'm going to solve this. Now when I look at negative 2/3, that is not a special triangle, so I know that I'm going to end up with a decimal answer for my thetas. I still have to figure out where do those two thetas live. So to do that, I draw a rotation, and I think about the cast rule. and sine of theta is negative. So I know that my two quadrant arm, or my two terminal arms, are in quadrant 3 and 4 at the bottom. And I'm going to figure out, well, what is my beta next to the x-axis in each of those pictures? And that's going to help me figure out the value of theta 2 and the value of theta 3. All right, so to find beta, whenever I want to find beta, I just have to make the ratio positive, and that's going to help me find beta on my calculator. So beta is going to be sine inverse of positive 2 divided by 3. And so I'm just going to type that into my calculator. I'm making sure that my calculator is in radian mode when I do that, and I get this lovely decimal here. All right, so now that I've got my beta, I can figure out my two thetas. I can see from the diagram, here's theta, the terminal arm for theta 2 right here. And that terminal arm is a pi plus a beta. So pi plus beta. And then for theta 3, it's all the way around the circle, but it's missing a beta wedge. So all the way around the circle, that's 2 pi, and then subtracting that beta wedge. And then I'm just going to type that into my calculator using my pi button and then adding the beta decimal. I get about 3.87. And that makes sense to me when I look at the picture that it should be a little bit bigger than pi, which is 3.14. So that makes sense to me. And then this one here, 2 pi, subtracting the beta, and I get about 5. Sorry, I don't actually have this one written down. I get about 5.55. And again, that makes sense to me. The whole circle is 2 pi's. That's 6.28 when I multiply 2 times 3.14. And so it makes sense to me that it should be a little bit less than that. And then I'm going to summarize. I'm going to write it as a solution set. So I'm going to say theta belongs to the set. And I'm going to list my 3 solutions in order. So from smallest to biggest. So pi by 2, if I think about adding it to this picture here, pi by 2 is this terminal arm up here, or this axis arm. So that tells me that it's going to be the smallest. You can think, well, like it's 3.14 divided in half, so it's definitely smaller than one of these two numbers. And then I've got my 3.87, 5.55. And that's the end of my set. All right, example 3, we're looking at a different strategy. This time we're going to have a trinomial that doesn't end up factoring. So we're going to use the quadratic formula. Again, I'm starting with the same thing. I need to set this equation equal to 0. When I do it, I'm going to reorder these terms so that the squared term comes first, the tan term in the middle, and then the constant at the end. So here I'm going to have tan squared theta coming to the front, then plus 5 tan theta. And then I've got 1 over here, but I'm going to add 2 to it when I bring it over, so it's plus 3 equals 0. Now, I'm going to try and factor this. I'm going to show that I did try and factor this. You can do the same thing that we did in the last question and let y equal tan theta, and then you would have y squared plus 5y plus 3. I'm going to leave the tan thetas and say that I'm looking for 2 numbers that multiply to the first coefficient, which is 1 times 3, and add to the middle coefficient, which is 5. And when I look at these 2 numbers, there's no pair of numbers that multiply to 3 and add to 5. So this is how I know that I'm going to use the quadratic formula. So remembering that the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, what does this equal? Normally we write x equals over here, so it's important that you know what this equals. Otherwise you're going to kind of lose track of where you're at. The variable in this equation, in this quadratic equation, is all of tan theta. It was tan theta here, and it was all of tan theta being squared here. So the answer to the quadratic formula is going to be tan theta. Or if you change to y's, you're going to have a y here, which you're later going to sub back in for tan theta. So I'm going to sub in my coefficients. So here I've got the a is 1, the b is 5, positive 5, and the c is positive 3. So I'm just plugging all of that in. All right, and then I'm going to plug this into my calculator. I'm going to do the first one with a subtraction in the middle here, and I get the answer negative 4 point. And for the second one, I'm going to plug in, I'm going to type this all in, but with an addition. And that's the decimal I got. Okay, so what do I do with this? Well, both of these ratios are going to help me find my beta. So again, I'm thinking about the fact that there are two possible answers. If the tan ratio is a negative number, there's going to be an answer in the S quadrant and an answer in the C quadrant. So I want to find the beta angle. So just like I did in the last question, to find the beta angle, I'm actually going to type in the positive of this. So I'm going to say that beta is equal to tan inverse of the positive ratio. And when I do that for this first one, I get about 1.34 for beta. And then that's going to help me figure out my theta 1. And theta 1 here I can see is going around to pi but missing one beta wedge. And that comes out to about 1.80. And then I can also find my theta 2, circling all the way to this guy. That's 2 pi but missing a beta wedge. And then typing that into my calculator, I get about 4.94. Okay, so that's for the first solution that we got there. Now we're going to take a look at what happens when tan theta is negative 0.697, blah, blah, blah. So for this one here, again, I can find my beta. Now, at this point, I'm like, uh-oh, I already used beta. And now I'm calling beta something different. So that's going to remind me that I need to label my betas differently. So I'm going to call this guy beta 1 and add those subscripts everywhere I've used it. And then I'm going to call this guy beta 2, just so I can keep using betas. And then again, for finding beta, the related acute angle, I just type in tan inverse of my ratio, but I make the ratio positive. And when I type that into my calculator, I get about 0.61. And then again, I can draw my picture. Again, the tan ratio from the beginning was negative, so I know that it's either in the S quadrant or the C quadrant. Just showing my thinking here. And then I label my beta. Here it is in the diagram. If you can fit a 2 on there, mine's really small. And I can figure out, well, what is the value of theta 3? Theta 3 is going to be pi minus beta. And typing that into my calculator, I get about 2.53. And theta 4, I'm going to add it to the picture, going all the way around to this final terminal arm. Again, that's a whole circle 2 pi, but missing a beta wedge. And then I'll just type that into my calculator, and I get about 5.67. And then I can write my solution set. So therefore, theta belongs to. And then I'm just going to reorder these guys so that they are in increasing order. So I've got those are my answers. All right, moving on to strategy 4. Strategy 4 is where we use an identity. Now, for this course, that could also include things like the double and the compound angle formulas. And that's what we're going to end up using in this question. So I know I need to use this when I have different ratios. In example 1 we saw it just happened to magically work out that I could common factor and it separated the two different ratios. But if you have two ratios mixed together, you need some way to get rid of the combination. I can also do it when I have different angles. So for this question here, I can see I've got two different ratios, don't like that, and I also have two different angles. So I'm just going to write a note about this. We have mixed ratios, we have a sine and we have a cos, and we have mixed angles. We have the angle x here, and we have the angle 2x here. So both of these things are bothering me, but if I start by changing the angle, it's actually going to fix both for us. So what I'm going to do is use the double angle formula. So I'm going to focus here on this guy. I'm going to get rid of this double angle. And so I'm thinking about my double angle formulas. And for cos of 2x, you might remember there's actually 3 different versions. Now, when I think about those 3 different versions, I'm going to think about what would happen. So if I use cos squared minus sine squared, that's one version, then I'm still going to have the mixed ratios. I don't want that. The other version I could use is 2 cos squared minus 1. But again, then I would have cos over here and sine over here. I'd still have mixed ratios. I don't want that. So I'm going to use that final version, the one where I have 1 minus 2 sine squared. So we're going to sub in that cos of 2x is equal to 1 minus 2 sine squared. That's our double ratio, or our double angle formula. And so now my equation looks like and then I can distribute the 6 into the bracket. And now when I look at this equation, what I notice is that there is a squared on the sign, so I do have a quadratic that I need to solve. So to solve my quadratic, I'm going to move everything over to one side. Oh, I did not leave a lot of room here. I hope you did. Okay. Just going to, oh, it's not letting me. Just going to slide that over. Hopefully you've got some room in your margin. I'm going to move over the 12 sine squared of x. And I'm going to move over the 6 and subtract it, so I end up with negative 15. And now I'm going to try and factor this. Now I notice that all of my coefficients are multiples of 3, so I'm going to take that common factor of 3 out. And then I can actually divide both sides by 3, so the 3's will cancel over here to a 1, and over here I'll get 0 divided by 3, which is still just 0. So really, I don't need the 3. It's not going to affect the solutions for x. So because I'm solving, I don't need it. If I was like graphing or something like that, then it would make a difference. So now I've got a quadratic. I'm going to try to factor it. It's a complex trinomial, so I need to ask myself what multiplies to 4 times negative 5. So negative 20, and what adds to the middle coefficient, which is a plus 1. And so I go through all my combinations, and I see that negative 4 and positive 5 are going to pass both of these tests. So I'm going to use them to decompose the middle term. And again, if you're really uncomfortable with all these sine x's, you can play that trick where you let y equal sine x, and it'll just kind of simplify this back to more of a grade 10 question. So the first term is staying the same, and then I'm going to use minus 4 as the first coefficient on my sine x, and I'm going to use positive 5 as the second coefficient on sine x. And so this really is the same as the line above, right? Because if I collected these terms, negative 4 sine x and positive 5 sine x, I would get positive 1 back. Now that I've got 4 terms, I'm going to group the first 2 and group the last 2, and I'm looking for a common factor. So in the first 2, there's a common factor of 4, and there's a common factor of sine x. And so I'll divide each one of these terms by 4 sine x. So in the first term, there's still a sine x left over. And with the second term, when I divide those, I'm left with a negative 1. And then with the second pair, I see that there's a common factor of 5, and I'll divide the 5 out from each of the terms, and I'm also left with sine x minus 1. Then I'm going to take that common bracket, factor it out, and then write the leftovers after I divide out the common factor. All right, so now I've got my two brackets. I can set each one of those equal to 0 and solve. So either the first one equals 0 or the second one equals 0. I can rearrange this to get sine x all by itself. Now I'm using my linear strategy, right? I'm isolating. I've got sine x equal to 1, so that reminds me of key points of the curve. So I'm going to use a sketch of the curve to help me. I'm looking for where does the curve have a height of 1, and there it is at pi by 2. And so my x value here is pi by 2. I'm going to call that x1 because I know there's more coming. Over here on the right, we're going to rearrange this again, so I have sine x equals. I'm going to bring the 5 over and subtract it, and then bring the 4 over and divide it. This is not a special triangle, so I'm not going to try and draw that. You might notice right away that this is not going to give any solutions. For those of you who don't notice it, you're probably going to try, so I'm just going to write this in green because you don't need to write this down because it's not going to work. You're going to try to find beta, right, the related acute angle. So when you try to find theta, you're going to do sine inverse 5 divided by 4. And when you type that in your calculator, you're going to get an error. So don't write error down here. I see this a lot. Like I'll see beta equals error. That doesn't make any mathematical sense. What this means is that there's no solutions. So why are there no solutions? Well, I'm going to think about this curve again. You're asking, when does sine x have a height of negative 5 over 4? Now remember, negative 5 over 4, that's negative 1.25. And so we can see right away that doesn't make any sense, right? The curve can't go below negative 1, so there are no solutions here. So I'm going to say since sine of x has to be greater than negative 1, greater than or equal to negative 1, there are no solutions. Now, there's only no solutions for this section of the graph. There is still this other answer. So my therefore statement is therefore x is equal to pi by 2. There is only one answer. All right, good luck with the homework for this section.